District.
One of the sciences is older than all the others by thousands of years. And if we include simply observing the heavens in the history of astronomy, then astronomy is truly as old as man himself. The basic foundation of modern astronomy began with the Renaissance. Having examined the theories of early astronomers from as far back as 400 BC, a handful of scientists would introduce some startling concepts about the heavens, risking their reputations and, at times, their very lives in doing so. Names like Copernicus, Brahe, Kepler, Galileo, and Newton would become the cornerstones of modern astronomy. Not the least of their ideas was the unspeakable heresy that the Earth was not the center of the universe, and that the sun and the stars and the other planets did not in fact revolve around the Earth. But if we push the clock back even farther, we have to assume that people have wondered about the heavens as long as there have been people to wonder.
Over the millennia, we've learned a great deal about the stars and the other components of the universe. Volumes and volumes have been written about the private lives of the stars. But actually, our understanding of these objects, the sun, the moon, the planets, and the stars, the beginnings of our understanding, goes back far before the time when people were even thinking of writing books, long before the idea of written language. It's not surprising this is the case, because people would simply look up into the sky and notice the things that are still out there for us to see. The daily motion of the sun and its annual motion as well, the cycles of the moon, and the planets, of course, which take longer. And the stars, too, turning around the sky with their nightly cycle, dependable like clockwork. In fact, that's just how they were used.
The ancients were aware of 5 planets drifting across what appeared to them to be a stationary background of stars. Mercury, Venus, Mars, Jupiter, and Saturn were all known to the ancients. And to most early civilizations, both the sun and the moon were simply 2 additional planets orbiting the Earth. A number of ancient civilizations developed some remarkably graphic notions about the universe. The ancient Hindus believed that the Earth was supported by 4 massive elephants. The 4 elephants were balanced on the shell of a gigantic tortoise, which in turn rested on a sea serpent in the midst of a forbidding bottomless ocean. To the Babylonians, the Earth was without a specific shape or dimensions. The stars were affixed to a shell far beyond the Earth, and the sun entered and left the heavens through a magnificent gate at the edge of the universe. The Egyptians believed that the universe was centered, understandably, on the Nile River Valley, and the mountains surrounding the valley supported the heavens. As with all the ancient civilizations, Egyptian astronomy was closely integrated with the Egyptian religion. Their religious image of the universe was that the stars were actually affixed to the body of the sky goddess Nut, which spanned the heavens. The sun god, Ra, was regally transported in a boat, rising and setting each day. Beneath Nut is the god of the air, Shu, and beneath Shu, adorned with leaves, was Geb, god of earth. The early Greek image of the universe was as imaginative as its predecessors. The earth was envisioned as a flat disk floating in a vast ocean. The stars were affixed to the inside of a hemispherical bowl which rotated above the earth. But with the development of the first intensive pursuits of philosophy and logic a few centuries later, the Greeks would eventually develop a number of amazingly accurate astronomical concepts.
The first people to develop a true theory of astronomy were the Greeks. They were an extraordinary people. One of the early extraordinary men was Pythagoras. And Pythagoras was, I suppose, easily one of the great mathematicians of all time. As he looked at the heavens, he was convinced that the heavens, as the earth, must be spherical. The stars, he thought, were carried around the earth. The earth was in the center of things. A spherical earth, a spherical heaven circulating above it. And he thought that, in fact, perhaps attached to each one of those little spheres, carrying each one of the planets, was some sort of a whistle. And as that whistle went around, it blew a note. It sounded the 7 different notes of the Greek scale. This is, of course, the music of the spheres. I suppose the most interesting line of development was the line that culminated, I'll skip over some possible intervening figures, that culminated in the ideas of Aristarchus of Samos. Aristarchus of Samos is frequently called, in fact, in a classic book by Sir Thomas Heath, was referred to as the Copernicus of antiquity.
Because he believed, as Copernicus did, that the sun was at the center of the universe, that the earth was but one of a number of planets revolving around it, which it did once a year, that the earth spun daily on its axis. I think that he was led to this concept as a result of some very ingenious measurements that he was able to make. He had a very sound method for determining the distance of the sun in terms of the distance of the moon. He also worked out a means of determining the distance of the moon in terms of the diameter of the earth. When he put all these data together, he found that the sun was several hundred times more voluminous than the earth. And it seemed therefore much more reasonable to him that the earth would be going around this large sun rather than that this large sun should be revolving around a stationary earth.
Aristarchus is therefore in the same mold as those who come along and devise new, more complicated systems to account for the variations that we observe in the motions of the member bodies of the solar system. Spheres are gone. Spheres are now replaced by simple geometrical lines. They're replaced by circles. Actually, there are 2 different approaches that emerge. The origins are obscure. Sometimes it's attributed to a man named Apollonius. Sometimes it's attributed to a man named Hipparchus, who was probably observationally the greatest of the Greek astronomers.
Hipparchus was the first astronomer who considered the brightness of a star as well as its position should be included in star catalogs. And the catalog of Hipparchus included this information.
300 years after Hipparchus, in the 1st century A.D., a Greek astronomer published an astronomical encyclopedia called the Great Syntaxis of Astronomy. The astronomer was Claudius Ptolemaeus, or Ptolemy. Ptolemy incorporated military observations of Hipparchus into a highly complex scheme of the universe with scores of circles which moved around even more circles called deferents and epicycles. But the important point was that Ptolemy placed the stationary Earth at the center of the universe, and the Ptolemaic system would remain virtually unchallenged for the next 1,400 years. In 1473, at the start of the Renaissance, the man who was destined to overthrow the Ptolemaic system, Nicholas Copernicus, was born. Copernicus was a highly respected scholar and churchman born in Poland who had studied canon law and medicine in Italy. Throughout his life's work, Copernicus had a strong, almost obsessive conviction that the laws of nature should and must be simple. So it's understandable that he would have been dissatisfied with the hopelessly complex Ptolemaic system of deference and epicycles. Eventually, after extensive studies of his own observations and those of other astronomers, Copernicus concluded that the basic assumption that the Earth was the center of the universe was also the basic flaw with the Ptolemaic system. In fact, the exact opposite seemed far more logical. That is, all the planets, including the Earth, were obedient orbiting members of a solar family. In the words of Copernicus, "In the middle of all sits the sun enthroned." The Copernican system explained the observed planetary motions more efficiently and simplified somewhat the complex and laborious Ptolemaic system, although not nearly enough to satisfy the personal drive of Copernicus for total simplicity. And in 1543, Copernicus braced himself for the inevitable reaction of the church and scholars around the world and finally published his masterwork, The Revolution of the Heavenly Orbs.
The Copernican revolution, as scholars have been realizing now for a number of years, the Copernican revolution wasn't a very complete revolution. Copernicus made one important decision. What Copernicus does is simply come along, take the Ptolemaic machine and say, okay, I'm going to, in fact, take the Earth out of the center and plug it in out here, and I'm going to take the sun from there and put it where the Earth was.
But what seems like a simple fact to us was a stunning revelation for the Renaissance mind. In the words of Martin Luther, "This fool wants to turn the whole art of astronomy upside down." 3 years after the death of Copernicus, in 1546, Tycho Brahe, a member of the Danish nobility, was born. In 1582, Brahe constructed a superbly equipped observatory on an island near Copenhagen with the financial help of King Frederick II.
And we can summarize Tycho Brahe's contributions just in a nutshell, and that is he was an observer. Copernicus, the theoretician, in his cathedral, theorizing about the universe. Tycho Brahe at his own castle, he was Danish royalty, in Denmark, observing the universe, concentrating on the planet Mars, because the Copernican theory was particularly inaccurate as far as predicting positions of that planet.
After his sponsor, Frederick II, died, Brahe moved his equipment and staff to Prague to work for Emperor Rudolf of Bohemia. And he hired a young mathematician as his assistant. His name was Johannes Kepler, and he was destined to capitalize on his employer's precise observations in a way that Brahe could never have dreamed.
Kepler was a very Pythagorean individual, very mystical man, appropriate, I suppose, for a man whose mother was tried as a witch. That's another story.
Whereas Tycho Brahe was Danish royalty, Kepler was the son of a couple of drunkards who in fact ran a saloon. I could tell you about the personal lives of these people. In fact, they're fascinating, but you can find that out on your own. Kepler was a believer in the Copernican system.
But although Kepler accepted the Copernican system, he felt that it had a subtle but basic flaw. While he admired the perfect harmonies of the spacing of planets and their sidereal periods in the Copernican system, Kepler was bothered by the fact that Copernicus had offered no explanation of this perfect relationship of concentric orbits. He began to suspect that the true orbits of the planets must be more complex than a neatly laid out series of perfect circles and epicycles. And in a stroke of mathematical genius, Kepler devised 3 laws of planetary motion, which refined the Copernican system from a general description of the sun and the planets into a precise mathematical formula.
Basic problem we have with observational astronomy is that we can't tell how far away things are in the sky. We can tell very precisely where they're located, their position, but nothing about their distance. And this is one of the reasons that the ancients had so much trouble figuring out what the planets were doing in the heavens. Well, Kepler was given a large number of observations of Mars that had been made by Tycho Brahe. And Kepler was clever enough to figure out a way to determine the distances to Mars. And with this information, with these distances, he was able to plot the orbit of Mars and then deduce from this the mathematical curve or the path that Mars followed around the sun, and to figure out the nature of the motions of the planets around the sun. And from this, Kepler came up with his 3 laws of planetary motion. His first law says that the orbit of a planet is an ellipse with the sun at one focus. The second law talks about how the planet moves in this ellipse. And it basically says that the closer the planet is to the sun, or to the focus of the ellipse, the faster the planet moves. A good example of this is with Halley's Comet, which moves all the way from inside the orbit of the Earth out past the orbit of Neptune. When it's out past the orbit of Neptune, the comet moves so slowly you could walk along beside it. When it's in close to the sun, it's traveling millions of miles a day. Kepler's third law of planetary motion relates the size of the orbit to the period, or the length of time it takes to go once around the orbit. And, for example, the Earth, which is about 93 million miles from the sun, takes 1 year to go around the sun. Jupiter is 5 times farther away from the sun, approximately, takes about 12 years to go once around the sun. And Saturn, which is 10 times farther away from the sun than the Earth, takes almost 30 years to go once around the sun. So these 3 laws of planetary motion allowed Kepler to describe what he saw in the sky, but he did not know why the planets behaved that way. And that was left for Isaac Newton.
In his own words, Kepler summarized his findings on planetary motion. The sun truly stands at the center of the universe, and if we observe, we are able to see the planets move, sometimes closer to the sun and sometimes farther from it. This movement is certainly not that of a circle, as we have for so long imagined, but rather the path of an ellipse. Indeed, not only does the sun stand at the center of the universe, but it is also the moving spirit. The very speeds of the planets are in fact determined by the force of the sun. Thus Mercury, which is nearer the sun, moves faster than Jupiter, which is farther away. The celestial machine is something like a clockwork in which a single weight drives all the gears. All the complex motions are guided by a single force. An Italian contemporary of Kepler, Galileo Galilei, shared Kepler's dream of defining a celestial clockwork governed by a single force. But since Kepler's work carried so many overtones of mysticism and astrology, Galileo, a devout Catholic, never took Kepler's discoveries about planetary motions too seriously. Instead, Galileo concentrated on terrestrial motions, particularly the motions of falling bodies. However, historically, Galileo is most often remembered for 2 other aspects of his work. To begin with, Galileo was the first astronomer to use the newly invented telescope for celestial observations, using a telescope that would be considered extremely crude by today's standards. Galileo was able to make detailed observations of the mountains of the moon, sunspots, the phases of Venus, and the 4 largest moons of Jupiter. His observations and sketches of the phases of Venus were strong evidence against the Earth-centered Ptolemaic system. And it was his discovery of the 4 moons of Jupiter that lent the most support yet to the Copernican system, by establishing that there certainly was another center of evolution in the cosmos, a concept that was in direct opposition to the classic view that the Earth was the one center of the universe around which everything else revolved. Galileo's also noted for his head-on collision with the authority of the Vatican. The problem was not that Galileo had offered his observations as support for the Copernican system. The views of Copernicus had already begun to be accepted by a small number of scholars, even within the church itself. But on a personal level, Galileo was obstinate and at times violently argumentative in his teachings, and had ignored a number of warnings from Rome over the years against stating that the Copernican system was indisputable truth. And in 1633, Galileo was publicly admonished before a papal tribunal, agreed to retract his heretical views, and lived out the rest of his years under house arrest in Florence.
An important point to make about Galileo is that his observations didn't prove the physical reality of the Copernican system. It made it more plausible, but there wasn't anything that he could point his telescope to. There's no observation that he could make and say, this proves that the Earth moves around the sun. There wasn't anything like that. It was a plausibility argument, a matter of reason, but he didn't have any proof for it.
Galileo Galilei died on the 8th of January, 1642. And ironically, within a year, Isaac Newton was born in the small English village of Woolsthorpe. And it was Sir Isaac Newton who would finally provide the missing link in the search for an accurate explanation of the Copernican system, which had eluded his Renaissance predecessors. And that is, why do the planets move in their regular orbits around the sun? What is the driving force? In 1687, Newton published the Principia, the mathematical principles of natural philosophy. It was a detailed explanation of Newton's remarkable theory of universal gravitation and the physical laws of matter, force, and motion. Some 200 years after Copernicus, Sir Isaac Newton had finally revealed the driving mainspring of the majestic clockwork that Brahe, Kepler, and Galileo had worked so long to explain, the force of gravity.
Copernicus gave us the concept of the sun at the center of the universe as opposed to the Earth. Kepler described the motion of the planets around the sun, and Galileo gave us the first telescopic observations which lent support to the heliocentric theory for the solar system. But it remained for Isaac Newton to explain why the planets go around the sun in elliptic orbits. And he did this in the 1660s with his tremendous insight, his discovery that gravity is a universal phenomenon, that it's not a force that's unique to the Earth. This force that we're all familiar with, that keeps me in the chair, that causes the ball to fall down, this is a force which is not unique to the Earth, but any two objects in the universe have gravitational attraction for each other. Even these two tennis balls have gravitational attraction for each other, and if there were no other forces acting on them, over several days they would actually come together just due to their own gravity. Well, Newton also discovered some laws of motion which bear on the problem of planetary motion. He said that if an object has no force acting on it, then the object will move in a straight line at constant speed. But if there's a force acting on the object, then that constant motion will be changed. The object will either go faster or slower, or it will change direction. And so now if we look at the situation of the sun and a planet, and ask what happens if there was no force between the sun and the planet, and the planet were moving, it would move in a straight line at constant speed according to Newton's first law. But if there is a force acting on this planet, and that's the force due to gravity, then that force will cause the planet to move in the direction of the force, and it will move in an elliptic orbit around the sun. Now, from what I've said, I think it's fairly easy to see that the orbit of the planet will be some sort of a curve. The fact that it's an ellipse and not some other kind of mathematical curve, that requires a great deal of calculation to demonstrate. But the point is that Newton, with this, I think, one of the greatest discoveries that mankind has ever made, namely of the universal nature of gravity, was finally able to solve this problem that was over 1,000 years old of the motions of the planets.
Isaac Newton brought together the works of all of his predecessors and dutifully acknowledged them as well. Newton, of course, is alleged at least to have made the remark that if I have seen further than others, it's because I stood on the shoulders of giants. He stood on the shoulders of Kepler and Galileo. And he took their work in motion and in planetary motion, and he synthesized it. And it was Newton who completed a Copernican universe by showing that, in fact, the planets move as they do because they move under the combined action of inertial forces and the new force which he determined mathematically and stated in a rather precise fashion, the force of universal gravitation. And with universal gravitation, we arrive at the completion, really, of at least one aspect of the story, and the Newtonian world picture becomes the jumping-off point for the 18th century Enlightenment. The Newtonian world picture is the world picture that continued to dominate the scientific view of the world until replaced by Einstein in the early 20th century. And even at that, even today, if you set about solving a problem in celestial mechanics, if you want to find the orbit of a satellite around the Earth, basically you'll do it by Newtonian methods, although as those have been changed and improved by subsequent generations. So that's essentially the story of the development of astronomical theory.
The earliest civilizations followed the natural inclination to place themselves and their limited worlds at the center of the universe. Eventually, that egocentric view evolved into a geocentric conception, which set the Earth unquestionably at the center of the universe. But it wasn't until the Renaissance that a handful of remarkable scientists would perceive that the planet Earth was only a single member of the vast solar family, whose motions are perpetually dominated by the sun.